Okay, hello. Question 15 as requested by Haya. Let's start. A ball falls through a vertical height of 0.6 meters before bouncing at point A on a ramp as shown. Show that the velocity of the ball immediately before the bounce is about 3 meters per second. You're going to have to make the assumption that the velocity just before it bounces is equal to the velocity after it bounces. And this assumption involves the conservation of energy. So your kinetic energy before the bounce is the same as the kinetic energy after the bounce. And we know that the mass doesn't change, meaning the velocity cannot change either. So it'll be the same velocity before and after the bounce. This assumption you make in physics unless otherwise stated. So yeah, so now we need to work out what is the velocity before the bounce. And we know that it was a height of 0.6 meters. So it had gravitational potential energy, and all of that got converted into kinetic energy just before it touched the ramp. So that's what we're going to do here. So we're going to say mgh, which is gravitational potential energy, is equal to half of v squared. Rearrange, v is equal to square root 2gh. So v is equal to square root 2 times 9.81 times by the height, which is 0.6. Let me put this in my calculator quickly. I'm sorry about my handwriting. I'm using a mouse. Square root. You get 3.431 meters per second. Make sure you show like at least 3-4 significant figures because it's a show that question. And that's around 3.4, sorry, just 3 actually, 3 meters per second. If you round this to one significant figure, you do get 3, so I'm happy with my answer. Kinetic energy is conserved as the ball bounces off the ramp. The ball bounces at an angle of 70 degrees. State the expression for the horizontal and vertical components. Let's go back to the diagram. Let's zoom in a little. So I know that the velocity as soon as it bounced, here's the direction. The velocity was 3.43 meters per second. And I want the horizontal component and the vertical component. Well, if this is 70 degrees, this has to be 20 degrees because that makes a right angle. So now I basically have a right angle triangle with hypotenuse 3.43, angle 20, and he wants the horizontal component and the vertical component. The vertical component is 3.43 sine 20. The horizontal component is 3.43 cosine 20. Okay, so let's put that there. So 3. Okay. Point A is 0.86 meters vertically above the ground and 1.23 meters horizontally from the end of the ramp as shown. Deduce whether the ball will bounce a second time, 4 marks. Well, to know if the ball is going to bounce a second time, you want to know what is its vertical displacement after it's traveled a distance of 1.23 meters. So here's the end of its horizontal displacement of 1.23 meters. You want to know where would the ball be vertically at this position. If the ball is above this position, which is, by the way, a displacement of minus 0.86 meters because you started here. So here is the displacement 0, and you have to go 0.86 down or minus 0.86 meters to reach this position. So if your vertical displacement is above this, then it would not have bounced a second time. And let me try and draw what I'm talking about. So if it is above it, then your ball could have went like this. As you could see, the vertical displacement is greater than minus 0.86. So it would not have bounced a second time. Maybe it done something like this. Your vertical displacement is positive now. I don't know, like maybe 0.2. So clearly it would not have bounced a second time. Or anything really where it goes above this point, so a higher displacement than minus 0.86, would have told you that it would not have bounced a second time. In the other hand, Okay, let's use a different color. If the vertical displacement was smaller than minus 0.86, then it would have took a path perhaps like this, which would have caused it to bounce again, or perhaps like this, again, bounced again, or maybe like this. Again, it would have bounced again. So if your vertical displacement is smaller, okay, so smaller than minus 0.86, oops, that's greater, smaller than minus 0.86, your vertical displacement, then it would have bounced a second time. Okay, so let's do that. Let's begin some maths. So it's a vertical sweep out because you want to know what is the vertical displacement at that point. So SUVAT. S is what you're trying to work out. Acceleration is always minus 9.81. The initial velocity was, what was it? 3.43 sine 20. So 3.43. Obviously, I'm missing two variables. And every time you're missing variables, you're going to have to use your horizontal component to help you out. And I want to know what the time is. I want to know how long did it take to travel 1.23 meters horizontally. And that will tell you the vertical displacement at that position, at a position of 1.23 meters horizontally. So to do that, I'm going to have to do a horizontal sweep to work out what is this time. Because remember, the time horizontal is the same as the time vertical for a particular position. So T is equal to S over U, and this is always the equation for a horizontal sweep. Displacement is 1.23, and initial velocity will be 3.43 cosine 20. Let me quickly put that on my calculator. I get 0.38. 0.38 seconds, okay? And I'm gonna store this, like the unrounded value on my calculator as, I don't know, A. Okay, so I'll store that as A. So now we know what the time is. The time is A, or 0.38, so let's just call it A. V is left, so you're going to be using S is equal to UT plus half AT squared. So that becomes S is equal to, and let's label the initial velocity U. Let's store it as the letter U or letter B or whatever letter you want to store on your calculator. So S is equal to U multiplied by T, which we called A, 0.38, minus G over 2, because this is plus G over 2 over here, but acceleration is obviously minus G, right? So minus G over 2, that's half A, and then there's T squared. T is A, so A squared. Put this on your calculator. Let me do that and see what do I get. Okay, so I got minus 0.26 meters, meaning, let me rub all this nonsense out, meaning it would have traveled a vertical displacement of, remember it starts here, that's where it started, would have traveled a vertical displacement of minus 0.26 meters, which is clearly above minus 0.86. So it would have perhaps done something like that, right? And clearly it would not have bounced a second time. Okay, I hope that makes sense. Bye.